I'm Lauren Madison in the Center for Energy Efficiency and Renewable Energy at UMass Amherst, and we are holding this training through the Massachusetts Energy Efficiency Partnership, which is sponsored by National Grid and Eversource. Thank you for joining us for heat pumps for engineers and energy auditors. We've been doing a lot of work on putting together this content that addresses a lot of the questions that we need to know when doing energy audits or doing calculations on heat pump operation and performance. And so I hope you find this useful. I sent out a link to the slides earlier, and I'll put that in the chat again in a minute. And we will send out a recording in the next few days, as well as information on how you can get continuing education units for participating. Throughout the session, you can put questions in the Q&A. Please use that instead of the chat. And we'll answer some of them in writing as we go. And then at the end, we should have time for discussion on additional questions or things that are more complicated and we want to discuss rather than write down answers to. And I think that's everything. So I will go ahead and introduce our speakers. Thanks to Jason Ganley from Mitsubishi and Alex Claremont from DXS, the New England manufacturer's representative for Daikin, for joining us today, and again for all the work they've put into developing this content. And I will go ahead and pass it to Jason.
Thanks, Lauren. Hi, everyone. Thanks for joining today. I know this time of year it's pretty busy. So my name is Jason Ganley. I'm one of the members of the commercial sales team for Mitsubishi Electric, located out of the great area of Boston. I've been doing VRF applications and technical support for about 4 years now, and looking to answer any questions you guys have. I do think a lot of this content is surpassed. We don't talk about it on an everyday basis, so this would be great for you guys moving forward. So hopefully you get something out of today. And I will be joining you on later slides, but right now I'm going to pass it off to Alex, and he's going to introduce himself. Thanks.
Thank you, Jason. Thank you, Lauren, for the kind introduction. Thank you very much, everybody, for your time today. So my name is Alex. I am actually originally from north of the wall up in Canada, and I'm actually a mechanical engineering graduate from McGill University in Montreal, and I've actually been with the DXS New England for 3.5 years now. This is our agenda for today. We're going to start off with just a quick recap of different types of heat pumps, efficiency metrics, selection of heat pump types and applications. Then Jason will take it over and talk about performance, modeling tools, data sources, some controls of operation as well. And then we'll take it back to talk about refrigerants and some special applications. And then Jason will close it off with some special applications on his end as well.
Alex, it's a little hard for me to hear you. Can you try adjusting a little bit?
Is this better?
Much better. Thank you.
Okay. Thank you, Lauren. So I mentioned that a little bit, but this does assume a basic knowledge of heat pumps. If you haven't watched Mike and Ike's presentation, we talked about heat pumps basics kind of 101. So if you haven't watched that, it's a good little recap, and the link is on the slide. Here's a quick recap of the different types of resource heat pumps that we talked about in the presentation. There's mini splits and multi splits. There's also package units, PTACs. These are often seen in hotels and apartments, and they actually take the heat from the room and then they throw it outside. Some of them also come with a heat pump function, which will throw heat from outdoors to indoors. These unfortunately don't work down to very low temperatures, so oftentimes they have electric heat in there as well. Our rooftops can also come with heat pump. They also don't work down to very low temperatures, so oftentimes backup electric heat is seen in them as well. Next, we have mini splits and multi splits. Those are more like commercial versions of an air source heat pump. A mini split is where you have a single indoor unit tied to one outdoor unit, and a multi split is where you could have multiple indoor units tied to one outdoor unit. With a multi-split each zone or each indoor unit will have its own control, but the system will have to be in the same mode that it's heating or cooling. Now, this is perhaps Jason and I's favorite topic, but now we're looking at one of the most common commercial air source heat pump, which is VRF for variable refrigerant flow. With these, every indoor unit has an expansion valve and can modulate how much refrigerant it wants based on the load. And the other unit will actually in turn modulate the amount of the compressor to adjust for the amount of refrigerant needed real time for each indoor unit, and hence the name VRF. These other units can be twinned up to 3 other units and increase the system tonnage depending on the design requirements. We'll go into efficiencies of these systems in a little bit, but these systems are really good at part load. At full load, they're pretty good, but they really shine at part load. And there's actually 2 different kinds of VRF. There's VRF heat pump and VRF heat recovery. Heat pump is also called a changeover system, and heat recovery is sometimes called simultaneous system. What we're looking at here is actually a VRF heat pump system, where the entire system has to be in either heating or cooling. Now, each zone can actually modulate how much cooling it wants, but for the whole system to go into heating, all the zones will have to be into heat. They'll have to be in heating. Next, we have heat recovery, and with this type of system, every indoor unit can actually be in different modes. You can have one zone in cooling, one zone in heating. There's actually a different component here that you can see, and there's those branch boxes. Branch boxes come in various different sizes, and they're actually they're kind of like the traffic cops for refrigerant, and they let either liquid or gas, depending on what's required for the indoor unit. And this is the most common type of VRF system used in commercial buildings. It depends a little bit on what type of space or indoor units you're looking at, but oftentimes it's preferred by the building owner or tenant to have this simultaneous heating and cooling ability. Now, VRF also comes as water source VRF. So instead of rejecting and absorbing heat from the air, this actually uses water. It's also available as both heat pump and heat recovery. They actually have the same distribution network as air source VRF, but the main difference is the heat sink or heat source. What we're looking at here on this slide are actually two different types of VRF system. On the left, you have an air source VRF system, which uses the air to absorb and reject heat, while on the right, you have a water source VRF system. On the left, if you see the air source machines on stands on the roof, and you see that black piping below it, those are the refrigerant piping going into the building, going to the branch boxes and all the indoor units. So water source VRF will have the same refrigerant piping going to branch boxes and indoor units, but the only difference is the machines doing the heat transfer. In the air source case, they're outside, but in the water source case, they're actually indoors in a mechanical space. So as you can see, the white piping there is on the right is the water piping from the rest of the building. But the black piping again is the same refrigerant piping. Now we'll get into efficiency metrics for most common types of efficiency metrics for air source heat pumps and water source heat pumps as well. In cooling, there's 3 main different kinds. There's EER, SEER, and IER. First of all, we'll talk about EER, which is the energy efficiency ratio, which is actually the efficiency of the system actually at peak load. Now, Jason's going to go into this in a little bit, but peak load is rarely seen. SEER is also a metric that's often used, and that's a seasonal energy efficiency ratio, which is actually an efficiency metric, which looks at EER over a range of conditions. Now, unfortunately, there's no climate-specific SEER. You have the same SEER rating for a unit in Texas and in New England, so it's not the best representation specific operation in every climate, but it does exist. Now there's also IER, which is an integrated energy efficiency ratio, which does look at different load profiles at different testing conditions to try to estimate the part load efficiency of the system. Now IER is much better, but it's not perfect, and AHRI 1230, which we'll talk about in a little bit, is planning to make changes to how IER is tested. So in heating, the main efficiency metric that's actually looked at is COP. So how many BTUs of heating can be outputted from a system versus how much electricity it takes to do so. Now these are currently measured by HRI as well, which is a testing association for all these types of equipment. Unfortunately, HRI only publishes COP at 17 degrees and 47 degrees, which is not really a true representation of our northern climates here up in New England. And there's actually talks about publishing COP data at lower temperatures. Unfortunately, there's also no part load COP, and it's similar to EER in cooling as it measures the heating capacity at full load. Now, ideally, there'd be an ICOP, which could look at part load COP. Now, there's also HSPF, which stands for Heating Season Performance Factor for smaller systems, which looks at the heat output for a heat pump, and that's similar to SEER, but for heating. So now we just want to talk about the COP comparison between traditional forms of heat and heat pumps. And as you can see here, heat pumps are more efficient because they don't generate heat, they actually transfer heat from one space to the next. Something as well to keep in mind with a furnace or a boiler. And the reason we have kind of COPs in that range is because that COP doesn't take into account the energy required for pumps or fans to actually blow or pump water around. Let's say it was a boiler. That COP is just looking at the furnace itself. So electric resistance heat is also just the baseline metric with the COP of 1. So now we just want to talk about a little summary of the different types of efficiencies. And HI 210 or 240 publishes the ER, SEER, and HSPF for smaller heat pump systems, so for capacity less than 65,000 BTUs. Now, HI 1230, which we'll get into in a little bit, publishes EER, COP at 1747, and SCHE as well. Now, we didn't really talk too much about SCHE, which stands for simultaneous cooling and heating efficiency. But as the name suggests, it looks at simultaneous operation for heat recovery systems. So it actually looks at part of the zones being cooling and heating, which should be looked at for heat recovery systems, as that does make the systems more efficient. So now we want to look at a true application for a true machine. And this is a 16-ton heat recovery. And what we're looking at here is actually a COP curve for that machine. So moving from right to left, we see that the temperature goes down. So it's plotting temperature versus COP of that machine. So as we move from the 50s, we're at about a 4.5 COP. As we go down to 47, which is a published AHRI point, we have a COP of 4. As we keep going down into the 30s, we have COPs right around 3 and 2.8, and actually at 17, the COP is 2.8. You see this bit of a dip right around 30, and we'll talk about that in a little bit. It actually is caused by defrost of these air source machines. And we'll get into that in a little bit. But the COP being 2.8 at 17, and then as it goes to 0, it's about 2.5 there on the graph. So something I just want to mention really quickly is that this technology of heat pumps has improved tremendously over the past 2 decades. And just a reminder that gone are the days of heat pump operation, with operation only down to 30 degrees. Nowadays, with inverter-based cold climate heat pumps, we have heating data down to -13 and -22 as well. So first of all, before we begin, we actually want to define cold climate here in the selecting heat pump section. So what do we mean by cold climate? Oftentimes we see this called out on floor plans by engineers, and we just want to define what that actually means, because it can actually mean quite a lot. There's a big difference between cold climate heating and cold climate cooling. These machines are really good at heating, but they can also be used in cooling applications in the wintertime. But those are two fundamentally different challenges. In low ambient heating, you're actually trying to extract heat from air. And in order to do so, effectively, you actually need inverter-driven compressors and vapor injection technologies. The two main points that you need. For low ambient cooling, you're actually trying to condense refrigerant at cold temperatures, which is actually too easy for the machine to do. So you actually run the risk of overcooling the refrigerant. Now, wind baffles, which is oftentimes a low ambient cooling accessory, helps with that, as it ensures that the cold temperatures of the cold wind does not make this process harder for the machine to do, and does not cause a refrigerant to come inside the building too cold. Sometimes wind baffles are also used to help with heating as well, as they do help with defrost cycles, which we'll talk about in a little bit. But essentially, the machine has to go into defrost, and wind baffles does help with that as well. Now, going back to heating, there's actually two different kind of models, or two different kinds of units. There's cold climate units with heating data down to -22. There's also standard heating machines with heating data down to -13. And the main difference between cold climate machines is the larger vapor injection compressors, and also larger coil surface area, which does result in more modules. Now, cold climate models, the -22 models, have also tested and designed their MCAs and MOPs of those condensing units at lower ambient temperatures. So they're tested at lower temperatures compared to the standard heating models. Now, both of these machines, both the standard heating machine and the cold climate heating machine, has cooling operation up to 122 degrees. So there's no real change in cooling operation. It's all the differences with the heating data. So another little chart that we're going to look at, and this is actually the difference between heating capacity of an 8-ton machine as a regular machine and as a cold climate machine. And both of them start out at 100% heating capacity. So that red line is showing the regular heating machine, and the blue line is showing the cold climate heating machine. And you see right around 25 degrees, the regular heating machine starts to have some sort of derated performance in heating capacity. Whereas the cold climate machine does tend to keep its heating capacity all the way down to 0 degrees. So the cold climate machine will have 100% of its heating capacity at 0 degrees, whereas the standard heating machine will have about 80% of its capacity. If you look at another point, -13, the cold climate model will have about 85% of its nominal capacity, while the regular heating machine has a little bit under 70%. Now, saying all this, cold climate units are not always the way to go, as they do cause footprint increases, and they do increase electrical draw as well. In our cold climate here in Eastern Massachusetts, we see kind of a mix of regular heating machines and cold climate, but the regular heating machine is more popular. Now, all that being said, let's say you are looking at an existing building and looking to retrofit it with heat pump technology. We've said this in the intro to heat pump module, but we always say it's best to look at your envelope before looking at applying heat pump technology. But that being said, let's say you do have an existing building with a high heating load. Does it make sense to go with cold climate models for the higher heating capacity, or should you use, if let's say you have an existing auxiliary heat instead, does it make sense to use that source of heat? Again, it all depends a little bit on the building, but as previously mentioned, cold climate models will have the higher electrical draw. So in some cases where you have a limited electrical capacity, a new transformer, it might make sense to go with regular heating models and use electric heat to radiate hot water. Now, Jason's going to touch on a few different ways to do this in a little bit, but just wanted to introduce that topic. Now we're staying on the topic of air source heat pumps, and now we're going to talk about defrost, which I quickly introduced in the cold climate slide. Now, the chart here on the right actually shows the heating capacity of a VRF unit based on outdoor temperatures moving from right to left again. You have the temperature going down and the capacity up and down. So right around as you get to 25 degrees Fahrenheit, you see that capacity starts to go down based on ambient temperature. The blue line in that is dotted there actually shows the corrected heating capacity based on defrost, which defrost will actually occur on the outdoor machine, at the outdoor unit outside, if it's doing heating in our climate. And you can see that capacity kind of gets affected because of the defrost. So when the unit's in defrost, its outdoor coil is actually going to get full of ice and snow, and water will freeze essentially on the outdoor coil. And that's not very good for the air source machine because it makes it difficult for it to extract heat from the air. So any air source machine really is going to form that frost on its outdoor coil if it's doing heating in our climate. Now that the machine's really intelligent and actually knows how to get rid of that frost, it actually switches the cycle over and it warms up the outdoor coil to actually melt that ice. Now, how does the machine actually know when to do that? It actually looks at its heat exchanger pressures and temperatures to know how good the machine is doing at exchanging heat. Now, we want to talk about another factor that these machines have in an accessory that's useful for them. It's those drain pan heaters. So when a machine goes into defrost, it's actually trying to melt the ice off its coil and reject it away from the unit. It's actually trying to go down all the way at the bottom and away from the unit. Now, when it does that, water tends to accumulate at the bottom of the unit. So drain pan heaters are often seen, and they prevent ice buildup on the machine by keeping the bottom of the unit warm, so ice doesn't form down there. Now, we talked a little bit about this, the blue line on the diagram, and how that takes into account defrost for the heating capacity. Well, it's actually possible to get continuous heating during defrost. And if you have, let's say you have two units side by side, it's possible to get one unit will be in defrost while the other one's still heating, which will provide refrigerant to the building. So it's still possible to get continuous heating during defrost with these types of machines. Next, we are changing gears and talking about water source VRF. So we talked about air source quite a bit, but where are water source VRF systems applied? Typical application is extreme cold climates, for example, further north up in northern Maine or up in Canada. These are commonly seen. Water cold systems are also used for high-rise applications, hotels or office buildings. And these machines do need to absorb and reject heat from a water loop, and that's oftentimes a closed loop, as seen here on the right with the boiler and cooling tower. But we are starting to see more and more applications where these are used in geothermal applications. Now, I mentioned extreme cold climates, and that's a typical application, but we see these used all the time here in our climates, and there's no harm for them to be used here. I'm just typically they're used up in more northern climates, but we are north, so they are used here as well. Now let me transfer it to Jason to talk to us about an application consideration and then performance.
Thanks, Alex. All right, so heat pump applications. Alex, myself, and anyone that works for a heat pump manufacturer is going to be the first one to tell you whether it's a good application or not. So I'm not going to be the bearer of bad news. There's obviously solutions for everything, but if we're considering certain indoor environments, these are the ones to consider. So one being high humidity. Right off the bat, VRF or heat pump technology is designed to could be controlled to dry bulb temperature, right? It does not control humidity, and a lot of the controls without any third party or large BMS systems don't read humidity. So in a high humidity setting, let's say 80% relative humidity, 85% relative humidity, that might not be the best application just because there's going to be a lot of sweating going on. That fan coil is going to be attacking a lot of the latent load and might not be able to produce the sensible load that it needs. So that's something to watch out for. Some kind of like cooler might not be the best application, but a way around that would be to potentially interlock a dehumidifier or a humidifier device to a fan coil unit. Just do a quick interlock whenever that fan coil is running. Then we have dehumidification as well, just so we have that liability, bring it back down to 60%, 50% relative humidity. Next indoor environment to kind of keep a close eye on is corrosive and harmful environments. Any kind of chemicals floating in the air, maybe it be, a manufacturing building of some sorts. I would try to stay away from that, placing like wall-mounted units on the walls, just because we don't know what the lifespan is going to be, and it might break down some of those coils. So we want to watch out for any damages on that, but looking at that, if there's a couple rooms that do have corrosive chemicals, then maybe think about using a ducted unit and ducting into the air, ducting the air into that corrosive room, and then maybe having a makeup air handling unit and exhaust that air. There's strategies around everything. And then lastly, something you should look out for when applying heat pumps is large box stores. First thing I think of is a Home Depot, really high ceilings, doors are always open. Maybe not the best solution for VRF. Typically with something like that, you might have rooftop units, DOAS systems pumping in about 70-degree air into that space. A way around that too, I'm going to talk about this a little bit later on in special applications, but there is a solution where you are able to take a third-party DX coil in a rooftop unit and connect a heat pump to that to control cooling and heating, right? So you're not installing, heat pump fan coil units in these large spaces just because there's not a lot of stratification and airflow. Can't really meet those requirements with, a heat pump, but you can with rooftop units and still utilize the heat pumps to provide that cooling and heating. So just something to look out for as you're designing systems. There are always solutions out there, so please ask as you're selecting products. So now we're going to talk about performance. So first thing first, when you look at heat pump data, right, you pull up a submittal, you pull up an engineering manual, you'll see certain testing conditions, and URL ratings and AHRI 1230 is what the equipment is tested by, right? So all VRF manufacturing equipment is seen in this testing results, right? So looking at the indoor temperatures, we're always going to see cooling mode tested to 80 degrees and 67 degrees, and then heating is going to be that 70 degrees. Right, so if you're looking through our submittals, those are the nominal capacities you're going to be seeing because that is our tested data, right? They also use certain piping requirements depending if it's ducted or non-ducted, anywhere from 25 feet to 75 feet, or for non-ducted up to 150 feet there. And then we set certain external static pressures as well, anywhere from 0.1 inch to 1/4 of an inch. So whenever you see VRF data, heat pump data, this is the testing that it conforms to. Now, we get this question a lot. The number one performance thing is, hey, at this temperature, what is your efficiency, right? You have 80, 67 and all the published data associated with certain EER, IER, and COP levels. But, those year round, those temperatures, are not seen that often. So you got to come up with a way to better describe how a heat pump operates. And as far as published data goes, IER is the best way to determine that. So the testing conditions at 100% are 95 degrees, and then you have your weighted EER values based on temperature bin data. So 75% load is around 81.5, 50% is at 68, and then 25% load is at 65. Those are all taken together, those EER values, and you come up with an IER value associated. And when you talk about part load efficiency, this is a great way to determine, hey, this is how efficient this piece of equipment is. But every building operates differently, right? Between the controls, the different types of equipment that's installed, whether it be heat pumps or third-party equipment. So everything operates a little differently. And if you are looking for more accurate representation of what that heat pump is going to be doing in the space, some of the best methods of approaching that is doing an energy modeling, or actually installing extra equipment to do energy monitoring as well, to operate your system as most efficiently as possible. And I know Alex has mentioned this briefly, but I just wanted to show you, what I'm talking about here. ER values are not the best for heat pumps, and it's because it's at, full load demand. So 100% loading, and it's going to be about 100% power consumption that it's tested at, right? So if you're looking at unitary equipment, EER is a good rating because it is very linear as it goes up and as it approaches, higher capacity, approaches, more power consumption. Right? IER is there to kind of show that VRF curve that we're seeing, right? And assuming that, hey, around 70%, we're actually below 50% power consumption, where, the unitary system is going to be 65, 70% of that power consumption. So IER really paints the whole picture of the performance of a VRF system. These are a little outdated, just kind of wanted to show you a graph. So, your SEER values in cooling are any equipment below 65,000 BTUs. Anything above that will be receiving your IER values. These are dated back to 2017, and they are increasing rapidly, as more efficient technology comes out. Now, some of our commercial systems are peaking around, 22 to 28 IER, so way above the standard benchmark of 14 in 2007. And this is the heating benchmarks as well. You'll see the COPs over here for the minimum efficiencies, dependent on the size of the equipment. And then if you guys are ever looking for certain types of equipment and what the efficiencies are, you can easily visit manufacturing websites. Or you can go on to this AHRI directory, which is searchable by manufacturer model. So if you have a model, right, what manufacturer it is, you can type that in, select the required things, and you can actually pull up, what we're looking at for your nominal, cooling capacities, heating capacities, and all your efficiency data. As far as manufacturing tools go, this is primarily the one that me and Alex would use on a regular basis, which is our equipment selection software. Right here, we're not necessarily focusing on efficiency. We are focused on selecting a working system, right? So this is what we do day to day. We work with consulting engineers, energy people, anyone that brings a project or an application to us. This is something where we're going to select a system and make sure that it is working and it fits the application correctly. So, we take your load calculations, right? Whether you do that, Excel sheets, any kind of software calculations and floor plans, and then we can kind of go in and, select commercial equipment, residential equipment, what have you. And one thing we can also kind of explore is diversity. So with a heat pump system, I don't know if we've really talked about this in the past, but with a heat pump system, you're able to really overconnect depending on what you're looking at. The two types of diversity we really look at are solar diversity and occupant diversity, right? Solar diversity, if you look at this building up here, right in the east, we're going to have, let's say 5 tons on the eastern exposure in the morning, and then we'll only have, 2 tons on the western exposure, right? And then as the sun progresses throughout the day, right, that load is going to switch, it's going to flop, right? So you'll probably have about 5 tons in the afternoon over here from solar gain, and maybe only 2 tons over here, right? So on a traditional system, you might say, all right, I have 10 tons of, or 5 tons of fan coils on this side, I have 5 tons of fan coils on this side, so my system has to be sized for 10 tons. So the sum of the peak, which is not the case. What we're looking at for a VRF standpoint is the block loads. So you can basically connect 10 tons of fan coil units, right, to a 7 or 8 ton condenser, and that can be seen as diversity because you're never going to actually have that full load at one point during the day. And same thing with occupant diversity. Primary example would be if you were designing an office space, right? You'd probably have 4 or 5 conference rooms in that office space, open office space, and single offices. So eventually, during at one point of the day, these conference rooms are going to be used. Maybe people migrate to the conference rooms, get out of the open office space, and those loads are going to fluctuate between who is using what rooms at what time. So you can size for the block what we're going to be seeing throughout a one day versus the sum in each one of these zones, right? So sizing is very important to us. And just looking at the submittals, the engineering manuals, and taking the nominal load is really not enough to get an accurate reading on what you're selecting. What we like to do is see the corrected capacities based on your temperatures, right? For heating, for example, if the air starts to get colder, it's harder to extract that heat out of the air, right? So you're going to have a D rate that's associated, and then also potentially overconnecting will have a D rate if you're connecting 130%, right? And also it includes your piping considerations. So correcting capacity is a big thing. And when you're starting to do projects and starting to schedule heat pump systems, make sure you include that corrected capacity onto your schedules. And as we move forward to electrification, passive house is becoming increasingly more popular. And really what the first step of passive house is weatherization, right? And, I do truly believe that should be the first step for every building. Make sure that you have the right insulation going in and everything's tight. And due to passive house requirements, as your building gets tighter, as your envelope gets tighter, the cooling and heating loads are going to decrease, right? So make sure when you are doing a retrofit that you focus on the envelope first, because if you don't and you just replace your heat pump system, you might be way oversized, which can cause operational issues such as short cycling. And then just remember, this is a comfort, cooling, and heating product. We are controlled to dry bulb. We're not doing any kind of process loads whatsoever. And using the software, Diamond System Builder or VRV WebEx, it really shows you, at worst case scenario, how your system is going to perform. So this right here, we really focus on, making it work, focus on the capacities, but, in turn, we do know heat pump technology is efficient as well. So we can talk about that a little later on. So when you do a selection software, make a working system, you are able to export all these things. If you do reach out to Alex or myself, right? So you can export your equipment schedules, system images, which is seen right here on the right-hand side, any kind of submittals, specifications on the products, Revit files, CAD files, anything you need, it comes out of this software. So a great tool to have when you are doing preliminary selections or getting closer to your 100% CDs. Some of the data sources that manufacturers offer are, submittals, pretty generic, but this is kind of the one hitter. Everything can be pretty much found on here. Some of the things are capacity ranges, right? So your guaranteed operating temperatures, your nominal capacities, external dimensions, weights. As you scroll down, further into a submittal, you'll see the electrical requirements, whether that be, MCA, MCOP, recommended fuse size. I'll just point that, whenever you see a recommended fuse size, go with that. Don't try to do any wire sizing or, breaker sizing based off the MCA. Always, if there is recommended fuse size, use that. And then also we have efficiencies rated at the bottom that are tested at that AHRI, 1230 standard. If you're looking for more information, you can't really find it on the submittal. All manufacturers have, uploaded engineering manuals under the certain equipment. And just these are some of the things that we like to offer and that you can find in here. One being corrected capacity tables. This is actually built into all the equipment software. But if you are looking for, certain power inputs and power ratios based on, drop in space temp or drop in ambient temperature, that would be the place to look, right? There's outdoor installation, what are the clearances? You have your piping parameters, what you need to follow, weights, center of gravity, and then also, sound levels. So there's a lot of information in engineering manuals that, you might not know or might not have in your submittals, your cut sheets. So when we're designing a building, right, what is the goal? This is a very basic definition. Everyone defines a little differently, but I like this one, so I picked it. So to construct a building is to construct a building that's structurally sound, energy efficient, and comfortable for its inhabitants, right? So, structurally sound, that is your structural engineers, that's your architects, right? Energy efficiency is, the majority of this crowd today, figuring out if this is an efficient technology, and then comfortable for the inhabitants. That is really, your end spec engineers, consulting engineers, and our manufacturers to make sure we are selecting the right equipment to have, a comfortable environment for our occupants. Walking into a house with no AC, you start to appreciate the little things in life. So how did we get started when designing a buildings? Way back when, what happened is we just didn't really think about the envelope too much, and we kind of just put up a building to put up a building, which now has gotten a little costly from an operational standpoint, and then also a retrofit standpoint. As we progressed, we started getting into hand calculations, starting to figure out insulation a little bit more and coming up with loads that way. That got pretty overwhelming and tedious after a while. So then we started using Excel. I'm sure some of you still use Excel to this day. Totally fine. I've got some saved Excel spreadsheets as well that I use from time to time. Right. But really what saves time and energy and resources even is energy modeling. So this is really what we're going to talk about. Time is money in a sense, and this is really what we use today. We got to get a sense of we need to know what loads we need for every building, and energy modeling is the best way to do that. So energy modeling tools, right? What is energy modeling? I'll just have you guys read this. Right, so it does a variety of things. The main ones that people use on a day-to-day basis are eQuest, Energy Pro, and Train Tray 700. Right, a lot of these, and I have heard complaints in the past that VRF hasn't been quite represented as much as we'd like to, especially in this day and age. So one thing I'll mention is VRF and Energy Pro, still uses that modified algorithm and supplemental calculations, which we're trying to avoid. So most industry tools, I don't know if they've already had, or they're starting to convert to Energy Plus based modeling tools. And what that does is the curve regression for major differences lie in ambient corrections for input power, the adjustments are rated full power for ambient conditions. So basically, it's taking the energy input ratio correction factor and really starting to integrate that versus, just supplemental calculations. So that's really starting to get integrated into all of these softwares to better represent, heat pump technology. So when you are looking to do an energy modeling, what do you need before you get started? First thing being first is your building location geometry. Are we dealing with a 2-story office building, 5,000 square feet, or are we dealing with a high rise, 22 floors? Really, what is the size? What is the square footage of your building you're working with? Building materials, really understanding walls, what kind of windows are you putting in, triple pane, double pane, whatever it is, U values of your material and your insulation, and then any kind of shading coefficients that go along, talking about southern exposures, northern exposures, what have you. And then general building operation. Is this a multifamily building where it's going to be running 24/7, people are going to need cooling and heating all the time? Or is it an office building where the hours are 7 a.m. to 6 p.m. and then after that maybe you can focus on some kind of setback schedule or what have you. All interior loads values. So we're talking lighting, plug loads, occupancy numbers, right, and activity level, right? Are we going to have 20 people in office space? Activity level, are we going to be sitting at a desk, or are we sizing for gym with a larger load? So we got to know all that information. Zoning requirements, how many zones do you need? Are you just going to have an open office space with one large zone, and the smaller office spaces put 4 exterior office spaces onto one zone, or you're going to have individual comfort and give them each individual zones, right? So figure that out. And then system types. If you haven't decided what system is best, then you can always use the model to help you persuade that and compare equipment accordingly. And there are so many benefits to energy modeling, but these are just some of them. One that we really care about is predicts the monthly energy consumption and bills, right? It is a prediction, but sometimes it can be rather accurate. And then also you can do the energy or the annual energy cost. Nowadays, annual CO2 emissions is a huge factor. I'm sure most of you have heard of electrification in general. People are asking, hey, how do we electrify our buildings? What I've kind of picked up on is the steps are going to be weatherization, making sure you're insulated, right? You have a good working envelope. Second step would be to upgrade your ventilation systems. Typically, the ventilation system in this area, you're going to have natural gas or hot water, right? So we want to get rid of that. We want to go to electric solutions, eventually heat pumps. And then you kind of look into your domestic hot water. Are we, using a natural gas fired boiler for domestic hot water? And then lastly would be your overall retrofit of, whatever you have installed in that space and replacing that with electric technologies. Those of you not familiar, Boston has come out with a performance standard for carbon emissions. And basically what we're saying is all existing buildings and new construction need to reduce their greenhouse gas emissions by 100% by the year 2050. And New York City is doing something very similar, and a lot of other, cities, towns, states are, looking this direction. And what it is, our temperature rise has probably increased by about 1 degree Celsius in the past 20, 30 years. And as soon as we start to approach that 1.5 and that 2 degrees Celsius, that's when we start to have natural disasters occur. Life gets, a little bit more tough in that sense. So we're trying to avoid that in the next, 25 years, 30 years by electrifying the United States. And then some other benefits, compare and contrast different efficiency options, talking about equipment, and then kind of figuring out what your return on investment is, your life cycle payback is on various situations. So this is some energy modeling that we did based on 100,000 square feet in a 4-story hotel building. Might not be too relatable if you guys don't work on hotels, but this is just showing that installing VRF in these cities was about a 0.70 cent, cost per square foot per year versus, a conventional split system, 4-pipe system, and a water source heat pump. And then if we look at it, K through 12, we're looking at about 36% less decrease, and this would be based on an 82,000 square foot school. I just want to mention also that VRF systems are used to significantly improve the EUI, which is your energy use intensity, right? So a lot of the time, VRF systems are popular in net zero buildings or looking to go net zero. And that's because you need an EUI that's roughly around 15 to 20 kBTU square footage per year, which also considers the use of solar panels as well. This is another manufacturing tool that we like to use. We kind of call it the equipment comparison tool. It shouldn't be held to real numbers like your energy modeling can, but this is a great tool that manufacturers have that you can easily reach out to us and say, hey, compare these 3 types of equipment, and we'll be able to do so and kind of print out a report. So just I'm going to quickly walk you through the steps in order to get this done. But what you do is add building type, your overall size of a project, and your location. Right, then you kind of select your code. What are we adhering to? And then if you do have access to your most recent rates, utility rates, whether it be electricity, gas, this can all be entered in here. Then you can type in your building type, total area, and then percentage of your floor plans, right? So let's say I'm dealing with elementary school. So I have about this many square feet of classrooms, office square footage, I have about, 7,200 square feet. Gymnasium takes up 3,600 square feet. And then there's a cafeteria or dining. So you break it up into different areas like that based on, usage of the school. And then you can go into existing equipment, right? So I can take a system that has a central VAV with a water-cooled chiller and a gas boiler, select that. And maybe I want to compare VRF, this existing system, and an additional system, so I can select one of those. And basically, we get this right here, which is an equipment comparison report. There's a bunch more information. I just wanted to show you 2 slides on this, but the kBTU square foot per year, and it shows you all these interior equipment, lighting, domestic hot water, pumps, cooling, heating, and shows you what the existing system looks like versus if you install VRF with the same utility rates. This is what you might be looking at for, operational cost savings. And also, I like this table a lot. It has your 3 different options. So you have, VRF right here, you have water source heat pumps, and then you have a 4-pipe fan coil system. And then it takes on, the first cost, comparing that versus the lifetime expense of the equipment, right? Meaning lifetime costs, lifetime utility costs, and then also lifetime maintenance that's associated with that. And lifetime maintenance is, the smallest cost because there's little to no maintenance that needs to be required. Indoor units just need to, clean out your filters, check your condensate drains, all that. Condensing units basically just need to be wiped down with water, and clear any debris that could be stuck in there. That's about it. But yeah, this is a great tool. A lot of manufacturers do have access to this. So if you are looking to compare equipment, this would be a good option. The last tool I wanted to share with you, it's pretty straightforward, but it does calculate COP. And it calculates this average COP, right? So this is just an Excel document that I put together where you can go into the engineering manual and look up your corrected capacities. So for this example, I have a 20-ton heat pump right here, and we're looking at the indoor temperature of 70 degrees Fahrenheit, right? So you go to the graph, you enter in your nominal heating input, right? And power, and then your nominal heating capacity associated with that. And then already this has been built in, has your bin data. So between 50 and 45 degrees, we spend about 689 hours at that temperature, right? So you can kind of go through, look at the hours spent, and then come up with an overall weighted average. So what you're able to do is go into the engineering manual, take on the input rating, take on the percentage of capacity that you get, enter all this into the power input and capacity, and then you can see your COPs at certain temperatures. And they're a little bit different for each heat pump depending on the size, but this is a general way to do that if you are trying to understand COP at a different temperature than your 47 and 17 degrees. All right. We'll do this section and then we'll take a 5-minute break to catch up with questions. But I believe Mike and Alex are both answering any questions, so keep on asking if you guys have anything. So heat pump controls. Don't typically talk about this a lot. We typically just talk about the equipment itself, but controls is a huge aspect to the operation of this equipment. So how do traditional building controls compare to heat pump controls? All right, so if you take a look at this, central plants are huge and expensive. Typically, you'll have cooling towers, chillers, pumps, frequency drives, boilers, even more pumps, valves, controls, pressure transducers, really everything. There's a lot going on in a 4-pipe fan coil central system here, right? But everything is built in on the VRF side, right? So, your cooling, heating valves, variable speed control for the compressor, and also utilizing linear expansion valves. You can pre-program a lot of things, web-based control axis, occupant, remote control. All of these are built-in components to a heat pump system that, you might need to add a little extra cost onto the control side when we start putting all these pieces of equipment together. So some of these traditional systems require custom water plant controls on every component, some custom engineering and programming for each installation to optimize the system and demand loads, and then expansive ductwork and controller network installation, right? So all these are separate components: damper, fan, reheat, actuator, airflow sensor, and controller. Whereas, all of these are, on the heat pump side, are built-in components. So what does that do? Some of the advantages: it reduces the actual infrastructure of the space. It is a faster deployment, pretty easy to install, less intrusive. There are internalized control systems, meaning, there is a built-in logic already in these heat pump systems. Zone and individual levels of comfort already built in, and also increases energy efficiency as well, because it's all talking to one another. So we're looking at traditional versus heat pump controls. As you can see, VRF, all we need to do is communication wire and add a central control panel, right? That then and there is all you need to add on, and the system will run completely fine on its own. Whereas the other side, you're looking at your traditional system, we're going to need a lot more controls and panels added on to control each one of these pieces of equipment. That just shows, from a heat pump side, there are rumors out there that VRF does come at a premium. However, people kind of leave out the fact that it's everything, communication wise is built in, and you don't need any really external controls added onto a project, whereas a project like this, you will. And this is just a diagram showing you, your communication wiring, right? So your central system, your outdoor units are connected, right, to a, central controller. And then from each condenser, you have, communication wire, daisy chained down throughout the building. And if I tapped into the outdoor unit, I could see what's happening in every zone. If I tapped into this local controller right here, I could see exactly what the condenser is doing. Everything is built in and has its logic built in. All right, so wanted to kind of break this down into different levels of control we can do when we're installing heat pumps, right? So I'm going to mention local controls, central controller options, integrating with third-party BMS, right? If there's existing BMS is already in site and you are doing a retrofit, how do we communicate to that? Manufacturer's fully functional BMS system, is that an option? And then manufacturer energy allocation, I'm going to talk about. This is, really getting into the energy monitoring side, which is very beneficial as we progress towards the future. And then quickly talk about heat pump changeover, why this is important, and then mention supplemental heating and, what you might need for that. So different types of local controllers here. If you install the heat pump system and turned it on, it would run how it is. It would run on return air temperature, right? Ways of sensing temperature is either the return, right? Your local controller has a temperature sensor, or you can actually, if you don't need any local control at that space, you can also include temperature sensors or thermistors associated, right? If you installed any of those, they would work on its own. But basic control, pretty straightforward. There's 6 functions. You have your on-off, you have your temperature, mode, fan speed, and vane direction, right? Pretty basic, on wall, local occupants can figure out what temperatures they're most comfortable at. There's also advanced controls. Maybe if you don't have a central controller that ties in all the equipment, maybe you select a, advanced controller for scheduling purposes, right? Basic controller doesn't have that, but maybe if you did want scheduling, you would be able to select one of these advanced local controllers. There's also options for occupancy sensing, humidity, light sensing, diagnostics. There's even wireless and Bluetooth communication. Right. So diagnostics, that's a great one. All of the fan coil units are going to be connected to your controllers. And if there is an issue, let's say you need to replace a filter, or there's a condensate, float switch that's tripped, that will go with a code directly to the local controller. So it'll notify, it'll notify the occupants that the system is off and not working properly. Right. And this is a simple system that you can set up. You have your condenser, you have your fan coil units with a local thermostat in each zone. Pretty basic. And then you get into a central controller, right? So, hey, I have, 56, 70 fan coils on this job. I want to communicate with it. I want everything in one central controller or one central location. This is what you would be selecting, right? So it can access all indoor units for operation, monitoring, and scheduling purposes. Each one of these controllers can hold up to about 50 indoor units, right? And then you can add expansion controllers on to get a total of 200 indoor units under one controller. It's touchscreen. You can play around with it and see exactly what the temperature is in each room and how they're operating. You can also go through the central controller and do prohibit and lockout functions. You can prohibit, certain modes, right? Let's say, it's shoulder seasons. People want cooling right now. You're not going to give it to them, so you can prohibit that mode for the time being. You can also prohibit certain temperatures being set. If someone's really cold or, someone wants to change the temperature way up because it's not acting, fast enough, which it does. It's just a misconception. But anyways, you can set temperature parameters to say, all right, in heating, my maximum is going to be, 72 degrees or 75 degrees. In cooling, we're not cooling below 67. And then there's different lockout functions you can do if you don't want the occupants touching the controllers, you don't want any access, you don't want them to have any access, then you can actually lock them out of the controller completely. There's a lot more different options you can do and set up. And then this is where you'd potentially add BACnet to connect to a BMS system, but it's also network compatible. You can take a static IP address, type that in, the web browser, and then be able to see your system offsite need be. So you can do all those controls just through this one central controller. You don't need any third-party integration whatsoever. If you install a heat pump, this is what comes standard with a manufacturer. Central controller can tie in all of these fan coil units and all the condensers. So integrating with third-party BMS systems, typically we are integrating with BACnet. That's kind of the most popular. And there are two ways to do that. I just mentioned one, which is using a central controller. You are able to purchase a BACnet license, enter that into the central controller, and then get a static IP address for integration. So that is the primary option. You get tons, actually pretty much numerous monitor and control points. You can do a lot with that. And then you're also able to do an Mstp connection using a small Procon device, BACnet Mstp. Typically with this, it's a one-to-one connection at the indoor unit control board, and hardwire that to the BACnet. Typically with this, you might use it on maybe a project with 10 fan coil units. Anything above that, you probably just want to go the central controller route. And this is what it looks like. This would be your Procon with the Mstp, right? You have your local controllers with the condenser, and then you have this Procon device that's wired to BACnet. And then the central controller would tie this large system together, right? And then you can add, and this would go, then this would go to, the BMS that would take care of, a rooftop unit or what have you. And from a manufacturing standpoint, the largest, set of controls you can add on a project is their BMS system, which is a Niagara N4 platform utilizing a DC8000 controller. Provides control, managed external devices over the network, presenting real-time information with web-based graphical views. So some of the capabilities that it can do is, demand response compliance. We got your advanced alarming, lighting controls, HVAC equipment integration. Can pretty much do it all besides, life and safety. We don't tie into that. All right, this is one of the big topics that I have today, which is what is energy monitoring and allocation? So most manufacturers do have a solution for energy monitoring. And what it does is basically, in simple terms, allocates actual electrical usage of the outdoor unit, right? So the outdoor unit has a certain kilowatts that it uses per month, right? Whether it's running in standby, and then also has a small indoor unit operating electrical energy. So all this is compiled together, and then it allocates based on internal system and other components that I'm about to talk about to different, in this case, it's tenants, right? A, B, C, D, and it'll give you an exact kilowatt usage. And then in some states, you can actually do billing purposes. But right now, I want to show you this because if you are looking to monitor part load efficiency, this is a great option to do that. Right now, as far as energy allocation goes for tenant billing, New York City does this and a couple other states do. However, most manufacturers, all the manufacturers in the Massachusetts area have not been approved for this. It's actually getting revoted on in September. It's the Act relative to energy conservation. It's 3361. And basically what that does is, approves manufacturers' algorithm for calculating the kilowatts used over a month span. That can be used for tenant billing. So this is kind of the layout we need to set up. A lot of people, if they're not interested in energy modeling, don't want to add the extra controls onto this, but it does make a lot of sense if you are interested in how your system's actually running, and then you can adjust, temperatures, any kind of controls later on once you figure out, where the energy usage is and at what times, it's at its most. But looking at right here, we have your VRF, built-in communication wiring. So in this case, we're talking about tenants. So we have tenant A, tenant B, all connected to one condensing unit, right? And then there is this PI controller, which is your pulse input controller that's connected to a central controller, right? So on an energy side, we have your red line right here. That is your outdoor unit electrical supply. So right here, you'd add in a current transducer This does need to be revenue graded about 1% down to 10% of the rated size associated with that. And this is connected to a kilowatt pulse meter, right? That basically requires a 24-volt battery supply. And this is basically calculating, how much kilowatts are used by this outdoor unit. And for this, you can actually connect up to 4 outdoor units onto one panel. And to get the most accurate results, we do require that this be the panel has to be a revenue grade meter or panel. All right, so this calculates the pulses, and then the pulse output gets tracked by the PI, gets converted into a certain language, and then this central controller over here is basically acting as the energy data storage. One more thing needs to be purchased, which is the software that does the algorithms built in, and it tracks exactly how much energy we're using and what fan coil units are using the most. So this is the setup, great for energy monitoring to understand your building fully, not just saying, hey, I have 28, IER ratings, we should be all set. If you do want to get more in depth, this is a great thing to set up for, energy monitoring. And eventually when, this gets approved for tenant billing, you can be using it for that as well. If you do have a multifamily or, office tenant application. Okay, last 2 topics under this section is heat pump changeover. So don't talk about this a lot. Typically we talk about a simultaneous system, which Alex mentioned is one of the more popular, commercial heat pumps, right? What you do is you set that to auto mode, and it adjusts in about a 2-degree span and chooses whether it needs heating or cooling in the space. All the, occupant needs to do is set the temperature that, he or she wants. So with that being said, if we are looking into a commercial heat pump, right, that does not have simultaneous heating or cooling. It has no auto mode. So if you set it to auto mode, it's pretty much going to error out. You need to select either cooling or heating mode. And with that being said, if you left it how it is, the bare bones changeover way is, let's say if I have a condensing unit with 4 fan coils on the project, right? What's going to happen is all 4 of those fan coil units are going to have to be in one mode. Let's say they're in heating mode, 1 fan coil needs cooling mode. All of those fan coils need to turn in cooling mode before that zone gets cooling. So there are ways and options to kind of make sure you strategically set up your system so it does change over properly. The easiest one would be using an automation panel or BMS system that can, look at the outside air, adjust the set points, and do a lot more features associated with that. If you didn't have a BMS system, scheduling is always a good option, right? You could do it by day, month, or year. Typically, you do it by year and say, all right, in October, we're going to heating mode. The condenser is staying in heating up until April turns around. We're going to be in cooling mode. And, if there are certain events where we see that it's going to be, 90 degrees, in March, we are able to, send those commands, switch it over to heat, switch it over to cooling for 1 day, and adjust it accordingly. But that's a good way to approach it. I also like the fact that, if you do, going back to an office application with a condenser and 4 fan coil units, if you're looking for a way to change it over, I do think having a central controller and dedicating a local controller to be the master controller or the representative group. Let's say, there's a CEO office and there's three other offices. That CEO, basically the boss is going to choose that mode and change over the system accordingly. So make sure when you are using commercial heat pumps that you do use some form of changing over the system. Just don't leave it how it is, because you will run into complaints and occupants are going to wonder why they're not receiving cooling or heating mode depending on the season. And Alex mentioned this briefly. I just wanted to introduce, how we do certain functions, or how would we introduce, first stage and second stage. So is auxiliary heat available? The answer is no. Then you might as well just think about using VRF as the sole source of heat. As Alex mentioned, we do have heat pumps rated down to -13 degrees. and all the way down to, negative 22 degrees. So VRF can be seen as a sole source of heat. But if you are in a retrofit and, you do want to keep your, steam heat or, anything like of that nature, maybe it's district heating. What do you have? If you don't have it, then use VRF, and you can use VRF as the first stage, right? And auxiliary heat is the second stage. Or if you do have district heating, hey, I want that to be the primary heating in this instance, you can use district heating as the first stage and then VRF as the second stage. And I'm going to quickly tell you, what to use in those two scenarios. So integrating with the existing system, I know I had a slide on this back, but this is kind of related to, two things, right? First thing would be if I'm using a heat pump system and I do not like any of the local controls that any of the manufacturers have, I do like this Nest or, a different type. I would select a thermostat interface. What I'm able to do is connect the heat pump to this Nest, and the Nest can control, the heat pump accordingly, right? So that would be one option. Aesthetic is big to some people. Let's do that. But the T-Stat interface also has dual points for staging equipment. So in the example where you want to use VRF as the second stage of heat, you would use this interface and put Y1 would be your district heat, and then if you did need more heating capacity out of that, then you would put Y2 or VRF on your Y2, and you get heating from both systems that way. So just the staging process. This would be the way to do VRF as a second stage of heat. And then supplemental heating, if you wanted to use heat pumps as the first stage, you could do so. And then you could add this 12 VDC relay that can adjust between 1.8 and 9 degrees. What that does is it connects to every fan coil unit and basically operates based on drop in space temperature. The default setting is typically 4 degrees. So in the case where it's wintertime, we're trying to set it to 70 degrees, the VRF system can't keep up, or someone opens up a window, right, and that temperature drops to 66. What's going to happen is this relay will kick on any third-party supplemental heating, right, kick on until it brings it back up to set point, and then it will shut off accordingly. These can also be controlled to outside air as well. So if I want to use my VRF system down to 20 degrees, and then I want to kick on my boiler for radiant heating, then you'd be able to do so. All right, so I know that was a lot of information. I'm going to give us a 5-minute break, and then we're going to go over equipment operation. So if you guys want to ask any questions now in the chat, please feel free to do so. I'm going to start answering some questions. If not, sit tight until 2:25, and then we'll give up and get back and running.
And when Jason says ask questions in the chat, what he means is in the Q&A.
Thank you, Lauren.
Thank you, Jason.
Jason, there's a question on why heat pumps are not a good applications for home depots. You touched on that a little bit. You want to talk about that, or once we come back?
Alex, give me a minute and then I'll address it.
Yeah, well, no questions at the end.
All right, so I'm just going to answer one question that Jim asked. Why are heat pumps not a good application for Home Depots? Similarly, buildings with high air change requirements. So what I was getting at with the Home Depot is, the ceilings are 30 feet plus, and with VRF equipment, there's not a whole lot of options on the fan cool side. Typically with something like that, you would install, concealed ducted unit. Max you can go is about 8 tons on that. And as we start talking about, how large of a volume a Home Depot or a box store is, typically with something like that, we're not going to have great stratification. And, for the amount of air that's needed, you're going to be sizing, large tonnages for VRF equipment. So, something like that, better practice would be to use your typical, rooftop unit for larger amounts of TFM. With an 8-ton ducted unit, you might be seeing, 1,000 CFM. So, for just a section of a Home Depot, you might have to install, 5 of those versus a rooftop unit that could do, 5,000, 6,000 CFM and deliver 70-degree air might be a better option. However, we've been doing this all the time. We're going to talk about this in specialty applications, but we are able to, retrofit those existing DX coils, connect Mstp heat pump technology to those DX coils and basically use, heat or cooling. And you can either control that to discharge air temperature or room temperature. So it's not necessarily, it's basically the overall size and CFM requirements versus, the air change process. But all right, thank you for the question. We'll start answering some more as well, and then we can always take questions at the end. So getting into equipment operation now. For those of you who've joined these presentations in the past, you've probably seen this slide, but this is very important when we are talking about equipment operation and what the differences are between traditional systems and your variable refrigerant flow systems, right? So looking at these charts, we're talking about your constant speed on-off compressors, right? So what equipment uses that? It's your water source heat pumps, it's your rooftop units, and your window ACs, those AC shakers, those window shakers. All those are kind of on-off, get your temperature and then turn off. So what does that look like as far as, energy and set point? If we are looking at your set point, we're trying to get to, 75 degrees hot summer day, up to 90. Right, so we turn one of these on-off compressors on, and then it ramps on and basically overcools, not making it that very comfort in the space, and then it shuts off. Right, the temperature rises, and then it turns back on and off. And what this does is, uses a ton of energy. Right, we're using power at 60 hertz and then turning off. So A, it's not very comfortable in the space, and B, you're using a lot of energy. Which we're trying to avoid, right? So a great example that I can see is, you walking your dog, right? You have a new puppy, and that puppy is representing the building load, and that puppy just wants to, take off, kind of dragging you along the sidewalk, and that's really what a single speed compressor is. You don't have much control. Hey, you brought your room down from 90 degrees to 75 degrees, but it fluctuates so much and uses so much energy. It's just not an efficient way of doing things, right? So we need that dog to slow down a little bit and get to a comfortable location where, it's an easy stroll down the street. And that's what your variable speed system is, right? Again, you have that set point, we're going down from 90 degrees. We're really ramping our compressor on. However, it does have a soft start on the compressor, which basically protects the compressor so it can have, longer duration throughout the years. That turns on, ramps way up. Gets exact, we're trying to get to the set temperature as quick as possible. And then over time, we are reducing the energy and still keeping that temperature where we want it to be, right? And the main thing that I'm trying to get out of here is on-off is not the way to go, and VRF and heat pumps in general are designed to be kept on, right? Because when it's kept on, we're gonna ramp down a compressor to a really low, hertz, and that's what saves the general electricity that we're using, right? So back to the dog scenario, you know, basically you try running with a dog, you know, hey, I'm gonna go for a run with a dog. You get to a certain point, you're like, all right, I gotta stop. But you know, that dog knows exactly, you know, how to walk, you know, it's not pulling you, they're walking on the leash perfectly fine, and you are at a comfortable pace at that point, right? So once you get to that set point, that pace, then you're good to go. And it makes you know, the experience of whoever's involved a lot more, you know, nice, I guess. Okay, so these are topics I've mentioned that we don't typically talk about when we, you know, mention heat pumps right off the bat. You know, we've all upgraded to, you know, VRF 20, you know, VRF 202, way past the 101, you know, standpoint at this point. So here I'm going to talk about some of the hidden energy save functions. They're not really hidden, it's just we don't talk about them on an everyday basis. I just wanted to let you know that these are options and are built into heat pumps more or less. So first one I'm going to talk about is energy save mode, which you can do with temperature setback there. Quickly mention building warm up. I know that comes up a lot. There is a flexible noise level setting. We are dealing with, you know, sound ordinances. And then there's two energy save functions called peak cut and then demand control that we're able to integrate into these systems. So energy mode or energy save mode is pretty broad overall. And what you'll need for this is either a local controller that, you know, has occupancy sensing. There are local controllers with brightness sensing. There's also ways you can, you know, go through a central controller and preset and, you know, set a date and time for some of these functions. And when you are doing energy save through a controller, you're only able to select one of these modes at a time. These are all available for you. Don't have to read through all of them. But some of the most common ones are, you know, set temperature offsets, right? For, you know, night setbacks. And then you are able to turn the fan speed down as well, which can, you know, be used. So some of the function settings that you're able to do is you can go in here, you know, say, hey, I have an office building. It operates between, you know, 7 a.m. and 5 p.m. Good, right? How do we check that? If there is a brightness sensor available on a local controller, what you're able to do is say, all right, when it's light out, we're going to be in operation. Okay. And then when you say your energy save mode, right, what are we doing? Are we doing, you know, a temperature offset, operation mode, on off? In this case, for an office, we're going to do temperature offset. You know, after 5 p.m., we are going to set it back, you know, 4 degrees, right? And then auto away time is every 10 minutes. So if you do have an occupancy sensor in your space, whether it be third party or, you know, use a manufacturer's occupancy sensor, this will go into, you know, a 4-degree temperature setback after 10 minutes of not seeing anyone in the space. Right, these offsets can be set between, you know, 2 Fahrenheit and about 8 Fahrenheit overall. And then you can readjust your auto away runtime as much as possible. So what you're able to do as well is if I did set this up and it is an office space, right, it goes on at 5 p.m. and at 6 p.m. I'm still working, you know, I'm adjusting the temperature, you know, occupancy sensor sees me. If I do leave, right, at, you know, 8 o'clock, this will adjust to the temperature set offset. But also, if you don't want to set that up, you are able to go through the central controller and set up block sweeps, which means you can, you know, group a certain amount of fan coil units on the floor, set that into a block, and then do every hour, sweep the floor, make sure that your temperature and, you know, mode are exactly where you want it to be. Because in a heat pump system, I haven't mentioned this yet, it's always last command wins. So from a BMS standpoint, if I adjust something on the BMS, it goes down, right? Funnels down, that's what the command is going to be. But as soon as an occupant goes to a thermostat, right, and they do have access to their local thermostat and adjust whatever they want to adjust, then that command is going to win. So it's always that last command wins when we're talking about control. Another feature that some manufacturers have, actually most heat pump manufacturers have, is an infrared sensor. Typically, you'd be seeing this with your cassette, but what's cool about this is it actually detects an occupant in rooms, right? So it's pretty much an occupant sensor, but it's a little bit smarter than that. You can actually detect, a human from your dog. And what you're able to do is set it up, hey, if we detect a person in the space, we can either have those veins flowing directly on the person, or if you don't like airflow going across your skin, you can also set it away from you. So pretty smart technology here. Isn't used a whole lot, but I did want to, point this out. And also counts the number of people, which can help with the energy save mode function. In this case, that's what I'm talking about. You have that sensor up here. It can tell the difference between, 100% occupied, right, versus about 30% occupied. And you can adjust it, adjust the system accordingly to, the percentage of the room. So in this case, if there's about 30%, the offsetting temperature is ±2, depending on the room. Right, 0%, and it's empty for more than 60 minutes, you can do a setback temperature of 4 degrees. In the case where you don't see anything between 60 and 180 minutes, you can actually turn the units off. For me, I typically don't like that. I like to see them running, even if you do set it back a little bit. But this is an option if you did want to turn it off. This space wasn't being used for a whole weekend, or whatever the scenario is. So building a warm-up. This primarily relates to schools. I get asked this a lot about schools. And what's the best practice here? I have talked about setback. This graph up here, the same from the other slide, is showing heating, but it's the same scenario or showing cooling, but it's the same scenario for heating mode, right? So as I mentioned before, heat pumps are designed for continuous operation, right? So we want to keep this on. We don't want to turn it off ever. We want to keep this set point where it is, 75 degrees, and we want to ramp down the compressor as much as possible to use as little energy as possible. That's how it operates. With a building warm-up, typically you do a larger setback, right? After 5 p.m., 6 p.m., hey, it doesn't make sense to heat the building to 75 degrees or 72 degrees. Let's set it back to 65 degrees, right? And I've heard some building owners do this, and then they start to realize that their energy bills are going way up. And you could probably guess that the reason for that is this is where we don't want to be. And with an hour building warm up, right, we're going to spend a lot longer time with your higher compressor speeds. Fans are going to be running at full volume just to make sure we meet this temperature. So this right here is what we're trying to avoid. And by doing an 8-degree, 10-degree setback for building warm-up purposes, this is going to draw a lot more energy, and it doesn't really make sense from a VRF operational standpoint when you're running that. So I know a couple contractors that have spoken to this. They said, hey, I left the set point on, same set point it runs throughout the day, throughout the night, and there was an incredible amount of energy savings associated with that versus going back to their old ways and starting building warm up an hour and a half, an hour before when school is about to start, when the doors open. And the compressor speed and amount of time definitely depends on the building and the weatherization of that building. But I would recommend, if you are trying to do temperature setback, stick to 5 degrees or less for a temperature setback, because you're really trying to get away from ramping this compressor up. We're really trying to just keep it at a steady compressor speed. Flexible noise level settings. This isn't necessarily an energy save mode, but this is a question that I also get asked a lot. This has to do with fan speed settings and dip switches that you can hit on the outdoor unit itself. But in the case where you live in Cambridge, or you're doing a project in Cambridge or other places that have sound ordinances, you need to be below a certain decibel rating at a certain time period throughout the night. You have your condenser ratings. You can find the sound ratings and power ratings on any submittal for a manufacturer. And if they don't adhere to what that decibel is throughout the night, what you're able to do is set a dip switch, and then reduce the fan speed setting, right? To get to that decibel that you need. The only thing with that is if you are reducing the fan, you're not touching the compressor, but you're reducing the fan, that does affect, that heat transfer on these outdoor coils. So it reduces the capacity as well, right? So the instance where, hey, 70% fan speed is enough to get to your sound ordinance level, but hey, I need 90% capacity at night for whatever reason, then you can set certain priorities. You can do, capacity priority, ramps the fan back up, gets the capacity you need, turns back to that, fan speed setting, or you can do, sound priority where it just reduces the capacity and, it just takes a longer time to heat or cool a space, So this is an option that, manufacturers have, heat pump manufacturers have that you can set up. Peak cut is something that we can use. I've already kind of described it, is very similar to the setup you'd use for energy monitoring and energy allocation. So what you do is utilize third-party energy meters to record energy use of the system. So every sensor controller does have the ability to track energy. However, it is not very efficient and it's not completely accurate as well. So if you did want accuracy into implementing peak cut, then you could set up a energy monitoring controls diagram, add all the equipment on. You're able to organize peak cut, and what that is, hey, I'm not trying to use over 800 kilowatts this month. Want to stick below that point. So halfway through the month you can set a limit. Hey, 750, 700. What that does is adjust the outdoor temperatures, the indoor temperatures accordingly to save a little bit of energy so that compressor is not working as hard, right? So you have control of that. You do need to utilize, your pulse input controller and that software that's associated with the energy allocation setup, right? So you can set different, 4 stages with kilowatt limits associated with your building. And you can do the same thing with your outdoor units, right? You have different options. So you can set the capacity, whether that be 100% all the way down to 50% with, percentages in between. And then you can do control times. Hey, I only want peak cut to be controlled every 15 minutes or this duration of 15 minutes. So you're able to do that as well. So if you are trying to reduce your kilowatts and, utilities are trying to, give you incentives on that, you can choose to do this to get some kind of incentive cash from that during, peak hours. And then you can do the same thing with your indoor units based on percentages. That was peak cut. And then the other option is demand control, which is, again, using that third-party utility company for demand control events. And what you're not doing is adding all that energy allocation, pulse metering on. You're actually just reducing the capacity of your compressors, right? And the utility company is controlling that. All you have to do is add an adapter at the outdoor unit itself, and then it'll give basically, voltages based on, where, what your capacity needs to be. So, in a demand control event, hey, utility company, you sign up for this, your utility company says, all right, you need to be at 50%. They're able to control that and set your compressor to 50%. Now, the one thing I'll mention is this does save energy, right? But this also does affect, the occupant's comfort within that space. If you're reducing, certain capacities at certain, times, then there's a chance that those temperatures, rise or drop, and it, the temperatures start to fluctuate. So it does get uncomfortable. So, you gotta choose your priority when you're doing that. Hey, do I need to save energy at this time? Or, am I worried about my, occupant's comfort in the space? So, demand control, same thing. You can limit to percentages, set up your control times for outdoor units and indoor units. Basically, a quick comparison is peak cut allows more local control. You know, an occupant, not an occupant, an owner or a facilities manager can, you know, take part in these energy events to reduce the kilowatts on their own time, right? It does include a lot more design consideration and hardware and time to set up. Whereas demand response is less installation. All it is an external signal, right? Connected to the outdoor units. But it does rely on the utility companies for the event. So utility companies will turn it to 50%, and then you might not need the capacity, you might not get the capacity that you need, you know, at certain times during the day. But, you know, these are both options you can do for, you know, saving energy at specific times. And with that being said, I will pass this off to Alex, and he is going to continue with refrigerants.
Thank you, Jason. We had a great question on refrigerants, so I figured that's something we would touch on now as well. We talked about that a little bit in the intro module, but we'll just kind of do a quick little recap and talk about refrigerants. Now, something to keep in mind is that every single type of heat pump actually uses refrigerant. We'll actually be focusing on refrigerants for comfort cooling applications in this part, but there's every different heat pump can use a different refrigerant based on its application. Some are high pressure, some are medium pressure, some are low pressure refrigerants. In this section, we'll be focusing on high pressure refrigerants. Now, refrigerants can contribute to global warming if they escape the system they're in and if they're actually not reclaimed. The global warming potential of that specific refrigerant was actually developed to compare different types of refrigerants between each other. And if those gases were to escape the piece of equipment, a refrigerant with lower GWP is actually not as bad for the planet. Now, as I mentioned, R410A is currently used in all new air source heat pump in VRF in the US, with actually a quick little exception that we'll talk about in a little bit. But R410A does not actually contribute to ozone depletion. Now, you might actually remember the days of R22, which was actually phased down in the 1990s and the 2000s, and actually officially phased out as of January of 2020. R22 can no longer be imported or manufactured. This was actually due to the ozone depletion of R22. Now, it's actually still possible to buy reclaimed or recycled R22, which is reclaimed from existing equipment, or actually, but you can actually buy drop-ins as well, just like Blue One, which is a drop-in for R22. Now, the phase out of R22 was actually one of the most successful global treaty worldwide. Now, let's go back to R410A for a little bit. The refrigerant itself is actually not bad, but it's actually the flame retardant additive that's actually added to the refrigerant, which can actually make it have a high GWP. And there's actually efforts to transition to lower GWP refrigerants, which we're going to talk about now. So some of you might be aware that the EPA actually tried to phase down R410A in 2015 and 2016, just like they phased down R22. But they actually got sued and they lost. And the premise was that the EPA actually didn't have the authority to phase down based on the global warming potential, but they were only allowed to do so based on the ozone depletion potential under the Clean Air Act. And this is actually where the American Innovation and Manufacturing Act of 2019, which was actually passed in 2020 as part of a COVID relief bill. And under this act, it actually gave the EPA the authority to phase down HFCs. It advised the EPA that the production and consumptions of HFCs should be reduced by 85% by 2036, which actually gets us right in line with the international phase down plan, which is actually called the Kigali Amendment. Now, manufacturers need to either use recycled or use some sort of their allowance limits that's provided to them. This actually started as of January of this year. And unfortunately, there's a bit of a loophole with anything that's manufactured in the United States, as it doesn't fall under this. And it does a little bit handcuff American-based manufacturers, but that loophole is being looked into. Now, one of the issues with building codes is actually that they do not allow the prime alternative for R410A yet if the refrigerant goes to occupied space. That prime alternative is actually R32 for high pressure applications. As I mentioned before, I mentioned high pressure because if you're looking at a water cooled cooling only chiller, it's easier to have lower GWP refrigerants as those are low and medium pressure refrigerants. Now, when you're looking to do heating, this is where you need those high pressure refrigerants. But currently, again, you cannot have R32 through occupied space. And it's going to be a few years before that's allowed at the federal level, and then a year or two to get it adopted by states. Now, it's estimated that we're probably still 5 or 6 years away from seeing R32 and VRF in large air source heat pump systems. Now, R32 has already started for small one-to-one split systems for mostly for residential applications in some states that allow it. Now, something to keep in mind is that there's actually no global warming potential, or just no global warming if the refrigerant stays in the system. So how do you actually reduce that risk of the refrigerant escaping the system? Well, proper install procedures actually play a large part in this, as well as the afterlife plan for recycling for the refrigerant. After all, the environmental benefits of actually using heat pumps technologies outweighs the impact and chance of potential leaks. Now, fear not, we've talked a lot about R410A and R32 coming up in the future. R410A is not going away soon. All these systems for the foreseeable future will be in R410A. It's going to continue to be available for the next few decades, just like R22 was available for a few decades for servicing of existing equipment. Now we're excited about the arrival of R32 as a next generation refrigerant with higher efficiencies and lower GWP and just overall less of it. But in the meanwhile, R410A systems are safe to install and they go through their life and without any issues. And we just have to focus on quality installs and keeping the refrigerants inside of them. So hopefully that covers, I know William had a question on refrigerants. Hopefully that does help that part going forward. Now we're going to start into some special applications and some emerging technologies that we are seeing out there with heat pumps. I just want to talk about this technology that's quite exciting and could be a potential solution for mass market applications, and that is wastewater heat recovery. And it actually could be applied to various different types of vertical markets, such as hotels, community centers, multifamily, gyms, just to name a few. And we have a couple of different diagrams here on the slide. And on the left, we're seeing a schematic for a traditional domestic hot water heating system. You have city water that's typically around 40 degrees, and it needs to be warmed up to about 140 degrees and held in storage tanks. Now, when somebody in the building turns on a shower or faucet, hot water is going to be sent from a hot water tank to the building. Now, 140 degrees is actually a little bit too hot for domestic hot water, so it actually gets mixed with city water to actually cool it down to around 120 degrees Fahrenheit. Then that water gets used by the occupant and then goes down the drain to the sewer system. Now, the sewer is not just composed of hot water, as it's mixed with cold water used for toilets and faucets, but the resulting water that's leaving the building going to the sewer is actually it depends a little bit on the building profile, but it's somewhere between 65 and 70 degrees Fahrenheit. Now, what we want to actually try to do is recover some of that heat before it actually goes into the sewer. And the first step of this is to implement the wastewater storage tank to capture the water to recover heat from it. Water that then gets pumped into a watered water heat pump, which we talked about in our intro to heat pump presentation. This machine actually transfers the heat from the wastewater to our domestic storage tank. With this wastewater recovery, we can actually hold some of the tanks at 140 degrees without using any additional heating source. So these types of systems come in various different sizes and shapes, and the smaller systems are actually water heat pumps, and they can actually, they're different modules. You can actually, they're pretty modular in size. And with the bigger systems, they actually come as split systems. So you have a machine that's separated from the main heat pump part of it. With all that being said, there's still some plumbing codes to overcome in Massachusetts for this technology to become popular, but we see this as being a big growth area in the next few years. Now, I do want to show some installation pictures of VRF and where they're being used today. So VRF used to be known as a technology that's to be used in smaller buildings and smaller applications. And we talked about that in a little bit, a little while back, but we are starting to see this type of technology kind of applied in quite large and very large buildings as well. So on the left here is a large high school that's being used to cool and heat classrooms. On the right is another application where VRF is a source of heat and cooling for a multi-family project. Now, these projects can actually get even bigger, and this is where we get into custom air handlers, where you have valve inside an air handler. And this is tied to VRF condenser units. And we call them kind of VRV-driven custom air handlers because all the cooling and heating is done by the VRF condenser units. Now, the size of some of these systems can get quite large, and in terms of VRF condenser unit capacity, it gets quite large as well. I do want to pass it back to Jason now for some more special applications that he will go through.
Thank you, Alex. All right, so I just want to wrap this up with a couple more applications. All of these are pretty important as we, proceed towards electrification, reducing these greenhouse gas emissions. So, looking at a building, we've talked about heat pumps by now. We've talked about their cooling and heating applications, right? But what else goes into a building? As far as electric solutions and what's out there. Ventilation is always one. Typically, in the Northeast, a lot of the time you'll bring natural gas or, have some kind of hot water that's maybe a boiler of natural gas. So, we're trying to reduce that as much as possible. And this right here, what I'm about to mention, is a great solution for, retrofitting these air handling units, DOAS units, which is using these heat pumps and retrofitting, DX coils. If you have a new construction project, you're also able just to, size a coil accordingly and, use these heat pumps to provide cooling and heating. So what is it? It's an interface that connects our heat pump units to, air handling units, fan coil units, or even like loose coils and, downstream ductwork. Anything you can put a DX coil in there, we could probably, retrofit into that using our heat pumps. So you can keep the fan and the housing the same. We just are going to take out, whatever that existing coil would be. So replacing gas and hydronic heating coils is primarily, what we've been seeing in the field as of recently. So what do we need for this? You have your, heat pump right here, placed on the outside. Typically it's air source. You can do these applications with water source, right? And then you have your, LEV kit or your LEV controller, more or less. And what that's made up of is, you have your LEV here, strainers on the side, and what an LEV or linear expansion valve is, it's located in all of our outdoor units. And what that does is it adjusts in 2,000 different positions. It's about 1/4 of an inch, What it does is it modulates the pressure of the refrigerant, to get the precise temperature that it needs. We're basically ripping that out of a fan coil and taking that here and controlling a DX coil. It also comes with 4 thermistors with your supply air, return air, and then your gas line and liquid thermistors. And then every, coil, every LEV, linear expansion valve, comes with a control box. Part of this is, you size your coil correctly, and you can control to either discharge temperature if you are, bringing your air down to 55 degrees and then add a reheat on, or you could, provide an air handling unit that's feeding a gym and provide, cooling and heating based on, room air temperature. So you'd have a, local controller in that space. Just showing you retrofit application that's been done. As you can see, there's an air handling unit right here that has a lot of existing chilled water and hot water coils going to the coil, right? Brought our, DX coil in. This is them contractors, taking it out of the box, moving it up closer to where they need to install it. What that is your refrigerant coil that will be connected to the heat pump. As you can see, these copper coils right here, that's where your linear expansion valves are placed, right? Contractors installing it, completely remove the hot and chilled water that was existing, right? And then you have your heat pumps on the outside. So these heat pumps are feeding these coils for this application. So just a great way to reduce, your greenhouse gas emissions using an efficient technology for cooling and heat. Lastly, if we're talking about a building, we have your ventilation, we have your heating or cooling options, right? But what about water heating? Typically you're just going to be using natural gas for that. As you can see, your space heating, is using majority of the energy, right? We have cooking that uses natural gas. And then this section right here is your natural gas or district heat, which is your water heating. So, is there solutions out there? Are there solutions out there on a centralized scale for domestic hot water? And the answer is yes. There is a CO2 hot water heat pump. CO2 is actually the baseline of GWP. It equals 1. So no global warming potential there. And what it is a heat pump that has CO2 installed right inside here, and then you have water piping going out to a heat exchanger, and then feeding storage tanks. And the whole mindset needs to be changed a little bit when we're talking about domestic hot water. Typically, you're going to have, a large source with, little to no storage. It's more of a demand response. That is not the case here. This is designed for small source and larger storage, right? So we're looking for a high delta T with a low GPM associated with that. And then we are storing enough water for that peak demand, whatever that is, how many GPMs it needs, at that time. So, it's targets up to 176. And after that heat exchanger, we're getting about 158. Typically with a storage tank, we're storing water around 140 to 150. And this does have low ambient operation built in, just like our, low ambient heat pumps is rated down to that -13 degrees. So it can produce hot water at that point, right? And, something that's nice is yearly Boston operation is right around 3 COP, which is very much more efficient than, any kind of electric resistance heater and, natural gas being burned. This is just an exploded view of this domestic hot water heat pump, right? You have your CO2 compressor right here. You have your external heat exchangers, variable speed fan, control box, control panels here, right? And inside you have your primary circulation pump, you have your flow control valve, water sensor, and then lastly, you have your twisted spiral gas cooler, right? So it's absorbing, it's basically absorbing heat out of the air. So that's why, it's absorbing, coldness out of the refrigerant and, heating up the water that way. And this is kind of what the gas cooler looks like. It is a twisted spiral gas cooler. What's cool about this is you have counterflow, so you have your water pipe going this way, then you have refrigerant piping wrapped around going this way. So you have a counterflow, and because that refrigerant pipe is wrapped around, increases the surface area, which increases the heat transfer in this pipe, right? So it's double wall construction, and you have basically 6 of these coils stacked on top of each other to make up that gas cooler, to provide, hot water to these storage tanks. And this is what the overall system looks like. It is a centralized system. There are, smaller split systems out there for an electric scale, but if you are trying to do a domestic hot water centralized system for your whole building, this would be an option for you, right? You have your primary side here. This is your heat pump on the outside. Then you have your hot water piping going to this heat exchanger. It's a really small heat exchanger, but it isn't necessary. If you are looking for it on the mass plumbing board, this is not what's rated on there. It's actually this heat exchanger that's there because it's touching the potable water. Anyways, on the secondary side, you're bringing this hot water in and it's maintaining these storage tanks, right? Keeping it around 140, 150. And then you have your pumps to get the right pressure and the right flow to ensure you're getting the right temperatures for these tanks, right? So you have the city water going in at the bottom of the tank, and then you have your hot side of the tank over here, and it flows into these tanks accordingly. And then that hot water is then sent out to the system, mixed with a mixing valve to get around 120 degrees, and then brought out to the space that way. And then the recirculation loop, typically you're going to have about 20 to 30% heat loss associated with that. So there's a swing tank included with electric resistance heat to make up those losses. So just a general, just this is out here. This is an option if you are trying to completely electrify your building. And this topic is, I probably get this question almost every day. And it's, hey, do you have any solutions for, existing high temperature water hydronic systems, right? We're trying to retrofit what's already there. We're trying to get rid of our boilers and the heat pumps, heat 160-degree water for space heating and maintaining loops. Now, the answer is yes. However, these are future products. And what I mean by that is a lot of these products are actually over in Europe, Japan, Asian countries. So they are out there. We're still working on bringing them to the United States. Right now, one of the options we do have is, if you are working with water fan coil units, is using a heat pump, right? An air source heat pump connected to a water heat exchanger, right? So you have refrigerant going to the water heat exchanger, and these are low temp hot water, so we can get up to 113 here. You can see this used for radiant floors. You can also use this to maintain your condenser water loops, right? Keeping around 90 degrees or whatever your design conditions are. You are able to use these air to water or refrigerant to water heat pumps to maintain that loop. So that is the option right now. Future products, the one I was just mentioning is, it's in the same family as the domestic hot water heat pump. However, the domestic hot water heat pump can only produce domestic hot water right now. The sister or brother-in-law that's coming to the United States in about 3 years has the ability to do domestic hot water and space heating. So this is the unit that's coming that will be able to retrofit your high temperature water hydronic system. You don't have to change any of the piping. You can kind of, plug and play, put this in and maintain that 160-degree loop. So that is a future product that's coming. It's not here yet. And also there's another product. It's not really for retrofitting, but it is a hybrid heat pump system. And what I mean by that is you actually use the same air source condensers, right? You'd see outside for traditional heat pump system. However, that refrigerant line is going into the building and connecting to this hybrid, controller. And what that's doing is actually having a heat exchange between refrigerant to water. And then you have 2 pipes of water going out to each individual fan coil unit. So that's manufacturer specific. You cannot add any, different types of water fan coil units. It's manufacturer specific. So we are manufacturing it. However, this is another solution for, reducing refrigerant in occupied spaces. for new construction. So a couple options that, are coming in the near future: hybrid heat pumps, probably a year out, less than a year out. And then that air to water heat pump that can do space heating and domestic hot water is coming in about 2 years, maybe 3 years. So that's it for, solutions as far as, heat pump technology goes. And then quickly just want to mention, I know Alex talked about this a little bit, difference between low ambient cooling and low ambient heating. Just remember that when you are specifying this equipment, low ambient heating is the actual condenser you select, the outdoor units you select, whereas low ambient cooling is the addition of wind baffles and low ambient units, right? So if you are working on server rooms, we do have precise temperature control with these, with a little bit higher, sensible heat ratios to basically produce that sensible load versus the latent load. But, we have options between 1 to 3.5 tons. And now if you just select this and you don't include wind baffles, you're getting about 23 out of it for cooling. After that, you don't really get much cooling capacity out of it. The wind baffles protect it, add basically a coat on, and you are able to cool to 0 degrees, all the way down to negative 40 degrees for an application like that. That's your low ambient cooling split. And then if you do have a bunch of server rooms, electrical rooms, all next to each other, stacked on top of each other, you can get into the commercial heat pump world and basically lock out the heating operations so this stays in cooling year round. In order to extend those, cooling lengths, you basically need to add a low ambient kit on, which is wind baffles and a motorized hood. And that will give you cooling capacity, 100% cooling capacity down to negative 10 degrees if you are looking to provide cooling year round. So those are just low ambient cooling applications. We do them quite a bit. This is, this is an option, whether it be split or commercial. And that just about wrapped it up. I'm going to have Lauren take over now. Thank you for your time.
Thanks, Jason and Alex. We just have some contact information here if you have any questions about incentives. And then we can go on to the next slide, and you don't have to take this information down because I sent out the slides earlier. And here's our contact information. A reminder that we will be sending out a link to the recording and information on CEUs, so you don't have to write me asking for them. Just wait for your email with that. And there, if you haven't looked at the Q&A, there have been a lot of good questions already asked and answered in there. And now I'll ask Jason and Alex to go back and address the couple questions that they haven't answered in writing. And then if you have any other questions, you can either write them in the Q&A, or once we get these answered, we can you can raise your hand and have some discussion. And I also want to thank Mike Reagan, also from Mitsubishi, who has jumped in and helped get a lot of the questions answered. So do one of you guys want to take on the couple questions here that haven't been answered in writing?
Yeah, I can do the first one. So I've run into instances on large commercial VRF installs, which cannot prioritize itself as a second stage to a hot water or chilled water valve through proprietary controls, so that should be investigated prior to a specification process. So to answer that question, you still are able to integrate heat pumps as a second stage. You do need a certain dual stage controller. This would be a third-party device that you can add on, where you have all the contacts necessary for that. As far as using heat pumps as a second stage, it can be difficult. You still have your inverter-driven compressor. However, the logic changes a little bit as far as selecting temperatures. Instead of adjusting it based on 2 degrees, selecting cooling or heating based on auto mode, what it does is starts at a temperature, sees where it goes, the differential between the set point and the room temperature, and then adds on capacity as needed in 5 minute increments. Another way on the cooling side to do VRF is, second stage of cool would be to actually install temperature sensors for the VRF system, have a central controller. So there's no, VRF heat pump controllers, and then have that connect to a BMS system and then do a temperature offset for both types of equipment, just to use VRF as backup cooling in some scenarios. I've done that recently on a lab space. So it's up to you. There's a lot of different controls aspects. It is good to talk about it before you start, putting on plans and waiting till the end until like 100% CDs. Bring that up as soon as you can, and we'll come up with a solution.
Agreed, Jason. Anything you mentioned? I don't think I have any more to add. Yeah, it's just possible to do it second stage or first stage. You just have to look at exactly how you want to do it in the sequence as well. So,
yep, the more information we have at the start of a project, the more information we can provide you.
somebody had a note on our offerings for air to water heat pumps, and Mike responded with, we're going to cover that in an upcoming preso. I also want to mention that our air to water heat pumps were a little bit more covered in our intro session. So if you haven't watched that, feel free to go back and watch that. It's a good presentation. We do talk about different kinds of air to water machines.
Alex, can you get a little closer to your microphone again?
Sorry, this is better.
Yep, thank you.
Okay. Another question about SEER and HSPF changes coming next year. Those are all, there's multiple changes, even IER changes coming to how that's tested and all that. So the equipment will have to be retested at different conditions by the different testing parameters that are being put out by Department of Energy.
Yeah, a lot of codes, standards are all going to be rewritten for new refrigerants, new technologies coming our way. So next 5 years, things could be totally different.
Are there any other questions? Okay, well, I don't see any raised hands or anything, so I guess we were all set. Thanks, Alex, Jason, Mike, and everybody for attending.
Thanks very much for putting this together. Hope everyone got something out of it.
Thank you, guys.
Thanks, everybody.